Hello everybody, my name is Robert Bücker. I'm the product manager for electron diffraction at Rigaku Europe, and today I would like to introduce you to the latest edition of our family of Synergy single crystal diffractometers, the XtaLAB Synergy-ED, as shown here. And this one is quite a different one from all the others in that it operates with electrons instead of X-rays. So I hope that I will convince you why this is useful and why this makes sense within our portfolio. So as you will know, the size range of crystals that you need for single crystal X-ray crystallography is limited to pretty much 1 micron. Here you see the range of our instruments starting from a tabletop one to a high-end one, and also an illustration of a synchrotron. But then there's this barrier which is really hard to cross using conventional X-ray techniques of 1 micron. Now, electrons interact with any sort of matter by many orders of magnitude more strongly than X-rays. So electrons can actually access exactly this regime of up to 1 micron, and only up to 1 micron, because any crystals larger than that essentially act as a beam stop for the electron beam because of the very strong interaction. Also, the specific damage caused by an electron beam to any sort of molecules is weaker than for X-rays, so you can extract full structural information from a single small crystal without entirely destroying it. And I think it is clear from that X-ray and electron diffraction are nicely complementary techniques, such that with this portfolio of instruments, you can study crystal sizes from the mesoscale all the way down to only crystals that are only like hundreds of nanometers large. This technique specifically is called 3D electron diffraction or microelectron diffractions, two terms which you can pretty much use exchangeably. So the measurement scheme is nowadays really exactly the same as you would be used to from a state-of-the-art X-ray diffractometer. So you have a crystal that you rotate continuously inside a beam, and you have a shutterless data collection on a detector. And due to this very, very strong interaction, get a sizable amount of signal inside your Bragg peaks. What's important is that this is quite different from what electron microscopists classically call electron diffraction, which is where you tilt your sample to like well-specified angles that are coinciding with low-lying zone axis of the crystal, and then take single micrographs. This is much more similar to X-ray data collection strategies, and can, in contrast to the latter, be used very well for structural characterization of any material. This technique has been invented in its modern form starting from around 2007 by several groups independently, mostly in Europe and a bit also in the US. And this leads to the unfortunate fact that it is known under a wide range of different abbreviations, but pretty much all of this is the same. So if you read any of those, it is essentially equivalent to that. And it has now been applied to a wide range of systems, pharmaceuticals, all sorts of small organic molecules, metal organic frameworks, even covalent organic frameworks, zeolites, minerals, natural products, but also samples from life science like proteins and peptides, especially ligand binding studies. So really everything you can make crystals from, essentially. So far, this has been conducted by only a dozen of research groups worldwide in transmission electron microscopes, which have been adapted to the task using custom software and very specific alignments, which of course is tricky, as this necessitates a research group which has sufficient knowledge both in transmission electron microscopy and in crystallography, and there are precious little few of those. So in 2020, Rigaku started collaborating with JEOL. And JEOL, as you might know, is one of the world's leading manufacturer for any sort of electron beam instruments, including transmission electron microscopes. JEOL also happens to have the headquarters just a few minutes by bike from the Rigaku headquarters. And we found out that the expertise of both companies is perfectly complementary for building a dedicated product for three-dimensional electron diffraction. Rigaku brings with itself the expertise for crystallography, also contributes a detector, but especially also all the software control for all the workflows. We provide the user training and all the scientific support that users will need to actually conduct electron diffraction. Whereas JEOL contributes the electron optical system, the electron gun, and also an entire ecosystem of auxiliary hardware, which allows for a wide range of sample types to be studied. And the Synergy-ED is the outcome of that collaboration, a dedicated electron diffractometer which is genuinely made for crystallographers and not for transmission electron microscopists who do a bit of crystallography on the side. It has a hardware design which has been designed by Rigaku and JEOL that is highly optimized for 3D electron diffraction. And the key thing of its design is a totally seamless integration of its hardware and its software, which covers it all from instrument control, data collection, data reduction, all the way to structure solution. And later on in our demo in the lab, you will see this whole workflow. So in terms of such an instrument, what are the requirements that we need to fulfill? First of all, submicron crystals are, of course, invisible to light, even under a light microscope. So any electron diffractometer must bring with itself also capabilities of screening for crystals in the first place in real space at a sufficient resolution. Next, electrons, because of their strong interaction with anything, can only propagate in high vacuum, which means we need a robust and fast system to get samples into vacuum quickly, which also means that samples have to be vacuum stable or have to be preserved, for example, by freezing them outside the vacuum and then inserting them afterwards. Another aspect that's important is radiation damage. As I mentioned before, electrons are quite gentle with any sort of matter, but still you need to extract a lot of information from a very small diffracting volume, so you need a very good level of automation to minimize any irradiation during screening and actual data collection. And even more importantly, you need the detector with the highest sensitivity you can get your hands on, not to waste a single electron on background noise. Finally, due to this vacuum geometry, which restricts you a little bit with how you can build a goniometer, only single-axis goniometers are available. So data usually needs to be merged from several grains. You, in this nanocrystal world, always have a lot of grains, so that's not a problem per se, but it's good to have some automation for data collection and merging from many grains at once. Now, let's have a quick look at how we solve this in collaboration on a hardware level. So on the inside of the Synergy-ED, there's an electron beamline, also known as an electron column, which has been designed by JEOL. It's called the JEOL GEM 2300-ED, which is exclusively available in the Synergy-ED. It is designed for electron diffraction, but retains some real space imaging capabilities, profiting from the massive experience in transmission electron microscopy for JEOL. And also, it has a projection system between the sample, which is sitting here, and the detector, which allows to set the distance or the virtual distance between the detector and the sample freely just with a click of a mouse on the interface. You will see later on how that works, and you will also see why this is important. Next, we have the detector here. It's the Rigaku HiPix-ED. This one is based on the Rigaku's proprietary HiPix hybrid pixel technology. It is pretty much the same detector as is on all our other Synergy instruments, just adapted for use inside the vacuum of an electron diffractometer. And as importantly, we have Chrysalis Pro running, which controls this detector and also the entire electron column, and also does the data reduction in real time and couples directly to further data analysis like structure solution and refinement, as you would expect from a state-of-the-art diffractometer. And again, you will see that later on in the demo. Finally, we have a sample stage, which you see here. So the sample gets inserted into vacuum from here. And here, because we have designed this together with Geo, who have a lot of experience with the vacuum stages, we have already a wide portfolio available with third-party suppliers for sample attachments that can handle cryo transfer, cooling inside the vacuum, heating inside the vacuum to above 1,000 degrees centigrade if necessary, inert transfer, even in situ systems where you encapsulate crystals between electron transparent membranes to insert some gas atmospheres, etc. There's really a lot available, and they are becoming more and more quickly. So just very briefly, the workflow in a 3D ED experiment is that already inside Chrysalis Pro, you screen for crystals on your sample that you inserted into the vacuum, collect diffraction data, and then directly solve and refine the structure in OLEX or whatever software you prefer. We also have features built in there to have a queued data collection where you pre-select crystals for data collection on a sample grid which holds the different crystallites, and collect many data in an unattended way, and also to merge all of those into one data set to overcome this potential problem of low completeness arising from the single axis GONIO. And with this, we get this under control quite nicely. Also, this you will see in some more detail later on in the lab demo. And even though this is a very, very young product, we already have quite a few publications with quite high impact journals with data collected on Synergy-EDs, either in the demonstration lab in Tokyo or the one here in Frankfurt. Just to highlight one of them, we did this one collaboration with the group of Neil Champness, which actually pushed this publication into Nature Communications, really into a high-impact journal, because of this additional data we could provide from a Synergy-ED, which turned out to be much stronger than the data that could be acquired for the same crystals on a synchrotron on diamond. So here, the Synergy-ED totally outperformed even a synchrotron. And by now, we have measured samples for many customers, over a wide range of different sample classes. Here you see just a few examples from all kinds of different systems. Here's some statistics. So we have more than 260 structures solved now, and actually increasing very, very quickly. And you can see that we cover a wide range of different classes of samples, of crystal systems, even including relatively long unit cell access, now also including more and more heavy elements. So this is expanding very quickly. Another thing I would like to highlight, which is actually not even included here, is that we can also conduct 3D electron diffraction on proteins. The way you do this is that you prepare protein crystals on a 3 millimeter sample grid in the same way as you would do in cryo-electron microscopy. So you apply few microliters of crystal slurry on such a grid. You quickly plunge freeze this into a container of liquid ethane, which will turn the water into vitrified amorphous ice. And then in the next step, either your crystals there are already small enough, or you can mill them down further using focused ion beam milling. So here you see microcrystals on one of those grids in a frozen state, and you can actually, as seen here, mill thin lamella out of it, and then insert it into a Synergy-ED. And here's just one of our first example data sets of thaumatin. which we collected up to a resolution of 2.15 angstrom, and then subjected this to our normal processing pipeline using Chrysalis Pro and structure solution using molecular replacement. We see some hydrogens in the map, and this really has only been our first attempt at it. Of course, in the research community, there are much more spectacular systems being studied than that, but we have a successful proof of principle that proteins work very, very nicely in the Synergy-ED. And this is one case where I would specifically like to highlight, again, this virtually settable detector distance, because, of course, with proteins, you have these long unit cells. In this case, it's 150 angstroms. So if we just kept the detector distance at what you would use for small molecules, the peaks would just be too close together to still integrate them. But what you see here is, again, the same data set. And for this long axis of the tetragonal unit cell, we could still nicely resolve the peaks here by tweaking up this virtual detector distance to 1.8 meters. And thanks to that, we could solve the structure and integrate those intensities nicely. And along this long axis of our anisotropic detector, the resolution limit is still quite a respectable 1.2 angstrom. So even for proteins, you can measure to such a high resolution if you're lucky enough to have crystals that deflect to such a high resolution, of course. And there are many more state-of-the-art advanced schemes that you can run with electron diffractions, and it keeps evolving rapidly. One of those would be absolute structure determination between enantiomers of the same molecule. This works fundamentally different than it would for X-ray studies, and I don't want to go into detail here, but it has been proven now that it works quite reliably for a wide class of systems. Another thing we're working on right now a lot is polymorph screening, because you can also imagine that a sample which contains a lot of these small crystallites is essentially just a powder sample which you measure on a single grain level, which means that if you have a certain mixture of polymorphs or some impurities in your sample, you can really disentangle all of them by measuring them in an automated way on a single grain level. This is also an advanced technique, and all of this is currently being implemented in rapidly updated versions of our software integration of the Synergy-ED. And with that, I'm done with the introduction. And let me add one final thing here, and that is that we don't only offer the Synergy-ED to buy, but we also offer service measurements at our laboratories, both in Tokyo and in Frankfurt, including data collection and also the structure solution. And if you want to learn more about this, just scan this QR code. This will lead you to more information. And now that's it for the introduction part, really. And well, let's move downstairs to the lab, and there we'll show you the thing in action. So, welcome to the Rigaku Europe application labs in Frankfurt, and welcome to the demonstration lab of the Rigaku XtaLAB Synergy-ED. With me here is my colleague Kai-Mi Ruang. He is an application scientist for X-ray and electron single crystal diffraction. And we are going to show you now in our lab how full experiment starting from sample preparation to data collection on the Synergy-ED looks like. So let me first show you the lab. Here you see the actual instrument. As you see, there's, well, honestly, not much to see from the outside. Everything inside this machine, except for the sample exchange, is computer controlled. So what you can see here is the point where the sample will be inserted. The only other outer part is up here, which is where you can fill in liquid nitrogen for a cold trap to improve the vacuum inside the diffractometer, which we are not even using right now because the sample we are going to use today is unproblematic in that regard. Here we see some auxiliary electronic devices, some other equipment which we are going to show you in a bit more detail in a second. But, well, first let's prepare a sample. So what's on the menu today?
So the sample that we will have a look today is Cryo. It's a commercial drug that you can buy. So what you want to take is just a little bit. You don't need a lot of powder.
So Kai already cracked up one of those pills for us and extracted the powder. And this long metal part here is the rod which will then be inserted into the diffractometer. What are you doing here?
I'm just grinding the powder even smaller. The grain size that we typically get is still too big for electron diffraction. So what we usually do is to grind them again with 2 glass plates.
This will also break up agglomerates. Great, they're a bit sticky. Okay, what's this?
These are the grids that we use. These are copper grids, and on top of the copper grids we have carbon film. There are different kinds of carbon films that you can have. This is just full film layer of carbon. We also have quantifolds, for example, where you have a wholly mesh inside of the small mesh that we will show you later on. And what you do now is you just dab the grid on your powder, get rid of the excess just by tabbing. And check under the microscope how the loading is.
We should also mention that this is only one way of several how to load your sample. You can also put it in a suspension and drop cast it. You can grind it in a mortar. So depending on your sample, there are a lot of different ways that you can use there. So now I suggest we take a look under the microscope. Switch to this view here. So you should now see close-up of this grid. You see this carbon foil, which at some point is a bit ripped, but it doesn't matter, suspended on a copper mesh. Each of those mesh squares is a bit more than 100 microns edge length. And what's important to note is that these little specks of dust are some crystallites, and the ones that you see are in fact already too big to be measured by electron diffraction, but it's still helpful to just assess if the loading density across the grid is reasonable, and to me it looks quite okay. What are we doing here? you see that at the tip of the sample insertion rod there is a narrow retaining part for this grid. It is spring-loaded and now held into place by a small screw.
So now we insert the rod into our refractometer. And here we have a switch. Now it's on air, so what we want to do is to change it to pump, and then the vacuum pump starts to pump down the environment.
The sample is now sitting in an airlock chamber, so we don't put it directly into the vacuum of the diffractometer, because then we'd have to break it every time we put it in sample. Instead, there's an airlock mechanism, so now it's in a pre-evacuation chamber, which will then pump down right now, and after it has pumped down, which typically takes a few minutes, you can fully insert the sample into the vacuum. While this is happening, we can show you something else. Yes. Which is this part here. This is another sample insertion rod, and this differs quite a bit from the one we've seen in that it has a little dewar mounted at its back, and you can just retract it from this mounting station where we place it to keep it clean. It's not in use. And what you see at its tip is that it also contains like a cradle where you would put your sample. There's even still one in, I see. And this can be covered through an actuator at the back of this holder. And this holder can be cooled down to liquid nitrogen temperature, and the sample can be cooled outside vacuum. And then you close this shutter and protect the sample from frosting once it goes again to ambient air, and insert it in this state into the vacuum of the diffractometer. Then you open it again, and you'll have a pristine cold sample that has not suffered from any icing or frosting while it was outside. What you see here is called the transfer station. This is where you would usually have liquid nitrogen in this dewar here at the top. And if you want to put a sample into this holder, what you would do is to have a sample that is already been frozen by just dipping it into liquid nitrogen. You can do that here or in an external foam dewar like this. Or there are different methods. You can also plunge freeze it in liquid ethane, especially if you have biological samples. And then in this station, under protected liquid nitrogen atmosphere, either liquid or under a vapor, you insert the sample in here, close the shutter, and then transfer it. Okay, and I think the vacuum might now have pumped down in the airlock chamber. Let's check. Yes, very nice. Okay, the sample is in. We now look at the screen at Chrysalis Pro. We see that the vacuum is still improving a bit. You see that blinking in orange. And I think we stop here for the video from the room and continue on the screen for the data collection. So now we see this CAP user interface. You see that the pump down has now fully completed of the airlock chamber, and we have inserted our sample into the vacuum. So Kai will now turn the beam on. The beam is turned on by engaging a heating filament on which the LAB 6 crystal that emits the electrons is placed, which is now heated to, I think, approximately 1800 kelvins. And now we should already see, like, slowly an image appearing on the screen. We are now in visual mode, which means we have a visual impression of our crystallites. What I can explain already now, while the current is ramping up, is that on the bottom left of this window you see a scale bar. So you see this corresponds to 1 micron, and you can see that those crystallites we have in the field of view already now are in a quite convenient size bracket, and we have a sample that, at least in terms of its morphology, is viable for electron diffraction. So we still further wait for a full ramp up of the current, but you see that this is actually a relatively fast procedure. We're almost there. And you also notice, of course, that the signal is getting stronger and stronger. So we have a lookup table where dark regions correspond to the highest transmission of the electron beam, so there's simply nothing. And now the first thing you would usually do when you have a new grid in the machine is to take an image for a mini-map, and this is what Kai is going to do now. So what is happening is that pretty much all the electron lenses in the column are switched off, and we get a very low magnification image of our entire grid, which has a essentially similar field of view as the image we had under the optical microscope. So we get a correlative information of the different scales, and we now can navigate on our grid using a point-and-click interface inside this mini-map. To navigate on the grid, there are various options. So what Kai is doing right now is to move it using a physical trackball we have for convenience at the operation console, which directly moves the stage in XY. But you also have a point-and-click interface, so you can actually see when Kai is clicking on some grain, the stage automatically moves there. And of course you will want to know if a certain grain diffracts, so to do this you just click this one switch, diffraction preset, which changes the value of, in fact, only a single lens in the entire electron optical system, which is enough to go from this visual mode to a diffraction mode. And we see that, in fact, this grain does give us a, well, not so shabby diffraction signal, so we might already consider collecting from this one. What do you think?
Yep.
Yeah, why not?
Sounds good.
Okay, so the next thing is with an X-ray diffractometer is to center the crystal on the rotation axis of the stage. So the way to do it is also pretty similar. You do it by tilting the stage to a certain angle, and you see on the bottom left of this window a visual indicator that we are now at a tilt of about 60 degrees. And then using again a point-and-click interface, this time with the middle mouse button, you can adjust the X position, the Z position of the crystal, so along the beam, because our column is vertical, it's the Z position, such that during the rotation it will remain within the field of view. What we should also mention at this point is that this green circle we have around the crosshair in the center indicates the region from which we will diffract. So the field of view for diffraction is actually not the full field of view we have now in visual mode, but it is smaller, and it is defined in the mode we are currently working in by an aperture which is sitting behind the sample, which is at first sight a bit counterintuitive, but it actually works exactly the same way as if you made the beam smaller. Kai, if you could click on, maybe click for a second on preview preset, we can have a look at this. So this is the diffracting region. This is this aperture, which we also now see is slightly misaligned mechanically. So it's best practice to check that, let's say once a day or even every few hours, that this is really still where you would expect it, but it's fairly stable. And now we can get back to this normal visual view. And of course, once we take the actual data collection, it will be reinserted. And I think as you have nicely centered the crystal, this is what we're going to do next. So you can click on diffraction experiment, and you'll be faced with a dialog that looks again as you would expect from an X-ray machine. You can already put the chemical formula in, or what you would expect it to be for the structure solution, which will happen online. You define the angular range for your scan, which we will use -60 to 60, the exposure time, which is given in seconds per degree, the scan width, which is just the angular wedge of each single frame. And this is one function that you will actually see in action in a second. I think it's better to explain once it's running. So now it's all set up, and we can start the experiment. Yeah, actually, thanks for pointing that out. You can also already see a prediction of the total time of the experiment, which will be 2 minutes, roughly. Now the next thing you will see is this option that Kai has just enabled, which is centering of the diffraction pattern. So because we have electrons and we can manipulate the electrons with electromagnets nicely, we can not only focus them, but we can also move them around laterally. So we can automatically move the direct beam to the center of the detector. Maybe you can change change this a bit. So you see now that it's very nicely centered, our diffraction pattern, which of course makes it easier for our data processing later on. Maybe you hear in the background how the gonio is moving. It's now at a starting position of -60 degrees. And now we see how the data is being recorded. You can already see that we have a unit cell estimate. I think it even was briefly in the proper Bravais lattice. It now jumped back to triclinic. Nevertheless, like usually this can go a bit back and forth in the first frames. But what you see is that already the data reduction has kicked in. So while the data is being recorded, you already have a data reduction at even first attempts at structure solution, which might be still unsuccessful, but should get better and better the more complete data we have. This is something that is totally unique to the Synergy-ED, and you will find in no other system for electron diffraction. And of course, all the experience that has gone into Chrysalis Pro is also applied here. So actually, as you've seen, the structure of the molecule that popped up is even already the correct one, but we are in the wrong space group. We're still missing a glide plane here, I think. So it's in P21. I think it's P21 over N. Is it? P21 over N. Everybody's darling. So I would guess that it will reduce to one molecule once it finds this glide plane. If not, we can nudge it a bit later on. Right, and what we can see here in Structure Explorer is that, well, as we have mentioned before, this is Gripostat drug is a mixture of paracetamol and ascorbic acid, and actually a bit of caffeine, but really not a lot, so it's hard to find that. And we actually see here that this time we caught an ascorbic acid, which actually may mean that it's even the proper space group. Could it be that ascorbic acid is in P21? Okay, no, then it's actually
structure.
Yeah, that's actually all right. So P21 over N would have been the right one if it was paracetamol, but as we have seen now already, it's ascorbic acid. So I was wrong, the machine was right. And yeah, as you see, we have a structure solution straight away. We have a data set with completeness of 88.7%, which is not that bad and quite okay to solve the structure. It's in a monoclinic space group, so that's enough. We have an R1 value of 16.7 without any further manual refinement steps, which for electron data is pretty good. And I'm sure if we now invested some time on manually refining it, we could get better, but we can also skip that for now.
Yeah.
Maybe.
As you can see, a few atoms are still misassigned, but yeah.
Yeah, I think we can live with that. Probably you all know that we could now directly transfer this solution into a structure refinement software, into OLX2. That's a click of a single button, and further refine this to assign the proper atoms, and also this will likely get our R1 value a bit lower. So Kai will pick another grain. That one?
Yeah.
Yeah,
it looks nice from the thickness.
Yeah. Yeah, you see that it's actually a bit translucent, which means it's relatively thin and should give us a signal that's relatively free from background. And yeah, it also diffracts nicely, as we can see here. So what we could either take another data collection or we do a queued one. What do you think?
As you like.
Okay. Yeah, we can actually, well, we could repeat, of course, now many manual data collections, but another thing we can show to you right now is a feature called the data collection queue, which means that we add many grains to a measurement queue, which we can then run in an unattended way. So you see here that the centering is still quite alright, even there, because we didn't move far. We maybe don't even have to recenter. Usually if you go to another grain, you would have to readjust the centering a bit. But I think it's okay now. So, same thing. We prepare same measurement. We basically can keep the same settings as the grain we have solved before. Looks all good. So we can now directly continue our search for well-diffracting grains. So that's a nice looking one. And as you see, we're still only navigating in a tiny fraction of that grid. So if you look at the minimap, we are still in one of those tiny grid squares of the copper mesh. We haven't even left this yet. So usually you measure only a tiny fraction of the real estate that you have available. So that fraction is more like so-so. So it might not be worth wasting measurement time on this one. On the other hand, especially if you have a queued data set, sometimes it's not worth to being super selective about it, because yeah, sometimes in this diffraction preset it might not look too great. Oh, that looks good. Actually, while we're at it, Kai, you could now show the options dialog, and this is actually where you set the nice. This is actually where you can set all the parameters of the diffractometer, like the the flux that you wish to have on the sample, which of course is important to determine the final dose. There are certain settings in this illumination box that you see here. Then you have the projection box below, which allows you to, for example, set this size of the region that you're diffracting from. And also, and this is like most interesting, is this box up here, which is where you would select the detector distances. And as I mentioned before, detector distances in this case doesn't mean that we physically move something, but that a zoom system, which is shown as projection zoom in this schematic on the right side, is set to different values. So now Kai has set this to, for example, 1015 millimeters instead of 645, and click on set current. And now if Kai closes that box, you will see something interesting happening, namely that you have the same diffraction pattern, but we just virtually moved our detector away, so we zoom into the diffraction pattern. For this diffraction pattern, this is a relatively pointless exercise because it was actually pretty well matched to the detector distance we had set before. But now suppose you want to measure, let's say, a framework material with a long unit cell or even a protein, then this becomes an absolutely essential feature. So we've measured proteins with this feature with unit cells as large as 150 angstroms or even larger. And you can do so just as you see with clicking one button going from one sample to the other without any physical intervention. And they are all independently calibrated, so you can do it all in one session even. Okay, so we actually didn't change anything in the options dialog, we just wanted to show it to you. And I think we can just put that one also on this queuing list. I think it's also a promising candidate. So now again, the centering procedure. So we see here, we have a bit of a walk-off. So maybe we should recenter this a bit. If we went a bit further from the grid, you would notice that this walk-off would be larger, of course. So what Kai is doing is symmetric centering, so checking it both at negative and positive values with respect to the perpendicular orientation of the grid to the beam. But as you see, it works quite nicely in both directions. It remains in this circle, which means it's just good enough. Also, I want to push it a bit further. No, we're even at 65 degrees. So we could actually, for this grain, even increase the tilt range a bit. And in this queuing feature, you can set the tilt range to, yeah, you can actually get the last use formula, you don't have to retype it every time. And for this one, Kai has found -65 to 63 is possible. The sample holder itself supports up to -80 to 80, but that depends on what specific sample holder you're using. For example, the cryo holder is -65 to 65, and generally, more complex your holder gets, the more restricted they might be in terms of their tilting range. But all holders that we consider or recommend will at least support, let's say, -45 to 45. And one more nicely diffracting grain just in the vicinity. Very nice. Often you have to search for a bit longer, but admittedly this is not a particularly complicated sample. It's one of our standard test samples, so we know it works nicely. If you have a true research sample, of course, often you spend some more time on finding grains that really diffract nicely. Okay. Same centering procedure. looks good. So minus 65 still sounds workable, looks workable. And again, we put this on our measurement queue. Okay, and I think we can now just start the measurement queue. So of course you can put as many grains as you wish. I think there is no upper limit even. So just click start. And it will now, and this is actually quite an important feature, not only recall the position of the stage that we have stored before, but using image processing, it will take another visual image, and in case the grid should have drifted a bit, or the stage should have drifted a bit, which can happen, especially if you have a cryogenic sample where the holder over time can drift a bit in its length, it will realign the visual picture of your grain with what it remembered from when you initially selected it. This turned out to be quite an essential feature, and now it's working quite robustly. Okay, and now we have the same procedure. And I suggest we just lean back and enjoy the show. Okay, so our queue is done, and this time we had actually 3 paracetamols in a row, so actually quite nice that we had an ascorbic acid when we did the initial acquisition. And you could also see on the right side maybe that for all 3 of them AutoChem could find the proper solution already during data collection, and we'll still have a look at 1 or 2 of the structures later on. Just before we move over to offline processing, we want to show you 2 more features which we think are nice and important. One is this button that Kai is already highlighting, and this button means that we can switch the operation mode of this visual screening mode between 2 different ones. One is this continuous stream mode that you've seen before, where you have a continuous video of your sample while you're screening it and while you're centering it. Of course, this also means that despite the extremely tight dose control that we have in this really extremely low fluxes of electrons that we use for screening, you can minimize this even further for very radiation sensitive compounds, because now we're in a mode where only short exposures are taken whenever necessary. So you see now that the image is frozen and the beam is actually blanked now. And now Kai clicked on another position. We hear, maybe you've heard it, that the stage moves to this other grain and another still snapshot is taken using really only a very, very minimal exposure. So we're talking here about a 2.2 seconds exposure time with a dose that, let's say, for electron microscopist standards is like totally off any limits. And even if you switch to diffraction preset, as Kai did now, it will switch the electron optics to this diffraction lens setting, take one brief exposure, and the same would happen now if we went for the centering. So whenever you apply a tilt, it applies the tilt. We'll then take a single exposure, and then for centering, if you go to the point-and-click interface, we'll also do it and take an exposure and so on. So the point to bring across here is you can do the entire workflow in this flash mode too. And honestly, if you get used to it, you don't lose much in terms of convenience. And for example, if you come from the world of cryo electron microscopy, this would be totally what you're used to anyway from the workflows you have there. Another thing we could show is that in cryo Pro, we have the option to export to quite a lot of different packages which you might want, and one that's specifically interesting for electron diffraction is PETS, which is a quite established package for electron diffraction data processing. Most of what PETS can do can be done on CAP directly, but if you would like to process in PETS, you can do it here as well. Another feature we can show, which is a bit related already now, is if you go on data reduction, is the dynamical export into YANA. You should be able to see it here. When showing the finalizing. So yeah, exactly. So this is actually, I think, quite important feature, which allows you to not only export HKL files with reflection intensities for use in standard refinement softwares, but what it can also do for you is to export a specific way of representing reduced electron diffraction data using a technique called virtual overlapping frames. This is now not important, the details. What's important is that you can directly import those data into YANA 2020, which will allow you to perform a dynamical data refinement, which is specifically interesting to obtain absolute structures directly without any intermediate software like PETS from data you get automatically from cryo Pro. And I think with that we're done for the online data collection and processing demo, and I would hand over completely to Kai now because he's the crystallography specialist to present you some of the offline data processing which you can do straight away after you have collected the data if you want to take the processing and the structure solution a few steps further beyond what the automatic pipeline is doing.
Yeah, thank you very much, Robert. So as you can see, the structure unit cell determination wasn't that bad at all. We could get the structure. This is paracetamol. There's a few atoms misassigned, which you can do now, but I want to show you how or what cryo Pro did in the background. So what it does at the beginning is always to do a peak hunting, so it harvests all the spots. the diffraction spots. It takes a few seconds. The next step would be then to do the unit cell finding. And in this case, we have already indexed almost 100%, 99.3% of all index spots. And if we have a look in the eval explorer, we could see that it matches up quite well to this unit cell of this monoclinic primitive unit cell of paracetamol. So the next step would be to do the data reduction. Because this one was a good data, we could just do the automatic data reduction. Again, it will take a few seconds. And again, we get the first structure solution with AutoChem. We can have a look on the structures more in detail again with OLEX2, for example. What we wanted to show you also is that because we cannot rotate the crystallites or grains fully like with an X-ray diffraction experiment, we need to merge a few grains from time to time. It again depends on the symmetry that we have. So if we have a look on this grain and upload it, we have a single completeness of 82%. And let's add also this one. And as you can see already, if we add just one more grain, we can improve the completeness.
So if it was a triclinic lattice, how many would you have to typically merge?
Typically it is like 3 to 4. Okay. Again, it depends on if it's a central symmetric space group or non-central symmetric space group. Yeah, and then it also depends on the orientation of the crystal or grain itself on the grid.
So sometimes you suffer from preferred orientation, especially for plate-like crystal morphologies, where you will often have to look a bit for crystals that are hanging in space a bit weirdly to get a full coverage.
So as you can see, the last 3 grains that we have measured, it was 969, 970, and 971. If we merge them, we get a completeness of 99%. So pretty good. So what we would do is then to give it a name. So for example, merge, output file name, click on OK. Now you have to process it again with GRAL. So you choose here, for example, merge that we just did. And now we have to do the refinalization again of this merge data. So we know it's a monoclinic P lattice, which is correct. Centrosymmetric P2 over N is also correct. And now just click on finish. It's done, and we could go for example to OLEX and solve the structure.
What you might have also seen in the input file to OLEX is that CAP will automatically insert the structure factors for electrons instead of X-rays for the atom species present in the structure. Yeah, you can see it here. So this will, especially for heavier atoms, significantly improve the quality of the data refinement, and this is taken care of automatically.
And now this is the merged data that we just processed with OLEX. As you can see, it was a quite straightforward structure. All the ADPs looks fine in this case. We have a 99.9% completeness. I over sigma R int are a bit high compared to X-ray structures, but that's normal. We have dynamic effects here in this case. So
I think for electron diffraction, you often have to, let's say, readjust your expectations concerning those metrics a bit. They are higher, but this is not because the data quality is worse, but just because there are systematic inaccuracies of the modeling of the data, and experience shows that the quality of the structure is still very high, so it's much higher than what you would expect from an X-ray structure with similar metrics. It's just that we are, let's say, using metrics that are coming from the X-ray world, which are, strictly speaking, not quite the right ones for electrons. This is, let's say, still a bit evolving in the field, but the structure looks very, very good.
yeah.
Okay, is there anything else we would like to show? I think we now covered everything from sample preparation all the way to the structure. It already took like a bit of time. We should actually stop it at this point, but I hope we could convince you how easy and straightforward the whole process is.
Yes.
So thank you for your attention and
See you soon.
bye-bye.
Bye-bye.